Hi, this is Trevor Evans, and this is a presentation I gave at TRI's first ever hair measurement symposium that was held in Princeton, New Jersey in June of 2017, and hopefully it's provocatively entitled, "Are we getting everything out of our stress strain curves?" A single fiber constant extension rate tensile experiment arguably represents the single most fundamental test we perform in the hair care industry. The remarkable mechanical properties of hair are a consequence of its complex internal structure, and therefore the measurement represents a probe into this otherwise inaccessible inner sanctum. Clearly we can't view the condition of the inner cortex structure in the same way we can watch the outer cuticle structure break down, but if the mechanical properties are changing, it must be because the inner structure is also being changed. And normally the reason we're performing these experiments is to investigate decreases in the mechanical properties as a function of exposing hair to all manner of conditions or treatments that are recognized to compromise the protein structure. And we're very grateful for the automated mini tensile testers that are commercially available and sold by the Diastron Corporation, which allow us to fairly easily run the relatively high number of replicate fibers that are necessary to produce the appropriate statistical confidence in our results. But these experiments do not spit out a single number or value that is indicative of a damage level. Instead, the outcome from testing each and every single fiber is a trace that looks like this, which we call a stress strain curve. Actually, strictly speaking, this graph is a force strain curve, which is obtained from the instrument measuring the internal forces that build up within a single hair fiber as it is stretched or strained at a constant rate of extension. However, it's recognized that hair's tensile properties have a considerable dependence on fiber dimensions, where, all things being equal, clearly a thick fiber will be stronger than a thin one. And for this reason, when performing these experiments, it's first necessary to measure the fiber dimensions, usually using a laser micrometer, such that the force units on a y-axis can be converted into a force per unit area, which is given the name stress. And there are a variety of parameters that can be extracted from such curves to provide information on hair's mechanical properties. I'm showing just a few here, but in fact, if you were to run the automated data analysis software that comes with the Diastron equipment, there are 18 different variables that are outputted for each and every stress strain curve, which perhaps begs the question, which one or ones give us the most information about how hair's structure is being altered? In fact, things get more complicated again. The graph on a previous slide was obtained by performing a dry state tensile test, but it's also very common to perform experiments on wet hair fibers. When individual fibers are placed in the sample cassettes of the commercial equipment, they are placed in a series of slots which can be filled with water or indeed any solution or liquid, and which allow experiments to be performed with the samples in an immersed state. And the reason for doing this is that the mechanical properties in the wet and dry state are supported by different regions of the hair structure. In a dry state, mechanical properties are supported by both the crystalline and amorphous proteins within the cortical cells. But in a wet state, water penetrates into the amorphous matrix and plasticizes away the contribution of this component. This is why the wet and dry state curves in the graph on the left here are so different. The wet state curve is reflective of the alpha helical protein in the microfibrils, while the dry state curve also has the properties of the amorphous matrix superimposed on top. This idea is very well entrenched in our discipline and dates back to a publication in 1959 by Max Fugelman. And so this model is widely known in our industry as Fugelman's two-phase model. So I think you can see there are benefits to performing experiments in both the wet and a dry state. But if we do so, well, we now have 36 different variables to consider, and the previous question becomes still more complex again. We hear a great deal from consumers that they desire strong hair, and when considering which of these parameters seemingly is the most instinctive representation of this property, I think we'd probably pick the break force. That is, how much force can a fiber be subjected to before failure occurs, and which is seen at the very end of the stress strain curve, just before the force plummets to zero. But of course, as we've just been discussing, strictly speaking, it should be the break stress that we're interested in, which is simply the break force normalized against the fiber dimensions. And also those who regularly perform such testing recognize that considerably bigger differences almost always arise when samples are tested in the wet state. In short, wet state tensile experiments just provide better sensitivity. And for this reason, I suggest that the vast majority of all tensile data that we encounter consists of wet state break stress results. And what I hope to show you in this presentation is that while this parameter does indeed work very well, there's also considerably more insight that can be obtained from consideration of these other parameters as well. So very quickly and for review purposes, I'd like to spend just a couple of minutes highlighting the significance of some of the terms that can be extracted from a stress strain curve. I find it very convenient to think about the mechanical properties of hair in terms of a spring. Hair is made up of alpha helical protein, which essentially constitutes tiny springs, and when we stretch a spring, at least within limits, we obtain an almost linear relationship between the stress and the strain. And the slope of this initial portion of our curve, which only stretches out to about 2% extension in the case of hair, is termed the Young's modulus, and in effect equates to the extensional stiffness of a fiber. If we continue to stretch, a point will eventually be reached where the spring gives or yields, and when the strain is released, the spring no longer snaps back to its initial length. This is called the yield point, and it's possible to evaluate the extension or strain to exceed this threshold. And similarly, we can also evaluate a yield force, or as we said before, more importantly, a yield stress. As we continue to stretch, our spring-like structure unfurls, with this molecular motion dissipating any force that might otherwise build up. And for this reason, we observe an essentially flat region in the stress-strain curve, which is often termed the yield or the plateau region, and which allows for the evaluation of an average plateau force, or as we said before, more strictly speaking, an average plateau stress. A major drawback in any single fiber hair testing is the high fiber-to-fiber variability. So back in the old days, before the advent of automated equipment, an idea for somewhat overcoming this issue was to generate a 15% load index. Firstly, the force required to stretch an individual fiber out to 15% strain was recorded. I think you can see this does not destroy the fiber, and the alpha helical structure can be regenerated by simply soaking in water. After a given treatment, the hair could be extended again to the same length to allow for the calculation of a ratio or index relating to this parameter before and after treatment. This approach does indeed lower the variability, and the diastron analysis software outputs a load at both 15 and 25% extension. But at the same time, this automated equipment makes it much easier to deal with single fiber variability by just simply running higher numbers of replicate fibers. And so this idea has essentially gone away over the years, but I'll be returning to an idea analogous to this a little bit later in this presentation. And so returning to further stretching a hair fiber, once the spring-like structure has completely unfurled, additional strain begins to deform the material making up the spring, in our case the hair protein. And so the force begins to rise again until eventually the protein chains fail, the hair breaks, and the force plummets to zero. And so parameters that can be calculated from this so-called post-yield region include a break force or break stress, a break extension, and occasionally, not so frequent, one might see the reporting of a post-yield slope or modulus. And so in short, parameters that are extracted from the low strain regions of the stress strain curve are reflective of the integrity of the alpha helical hair protein structure, while at the high strain regions we're measuring properties relating to the protein chains themselves. And strictly speaking, this spring structure analogy relates to wet state testing, where the contribution of the amorphous protein structure has been plasticized away, while in the dry state the contribution of this component becomes superimposed over the top of the spring behavior. We said earlier that wet state tensile testing experiments provide the best differentiation between hair samples that have been exposed to various insults and treatments, and to illustrate this point, the graph on the left shows dry state break stress results for hair with different levels of bleach damage. A 1 times 6% hydrogen peroxide treatment lowers the dry state break stress by about 6%, while 3 treatments with a 9% hydrogen peroxide solution lowered this parameter by around 11%. However, the graph on the right shows that the 6% treatment lowers the wet state break stress by about 12%, essentially double that of the dry state testing, while a 3 times 9% treatment produces a 29% decrease in the break stress, approaching 3 times that of the dry state testing. For further illustration, the graph on the left shows how a single treatment with a commercial relaxer product lowers the wet state break stress of hair by around 25%. The damaging nature of these highly caustic formulas is well known, but possibly somewhat less well known is the highly damaging nature of the formaldehyde-based so-called Brazilian keratin treatments. The graph on the right shows the wet state break stress of hair declining by about 30%, which is especially interesting given that the mechanism of action of these products is commonly thought to involve the formation of additional cross-linking within the hair fibers. And so just two more graphs to illustrate the usefulness of the wet state break stress. The one on the left now shows declining results for hair exposed to increasing levels of UV damage via an accelerated weathering chamber, while the one on the right shows an especially sizable effect relating to the repeated treatment of hair with a commercially available straightening iron that was set to its highest setting. And so the results on these most recent slides show the wet state break stress changing in an expected and progressive manner as a function of well-known damaging treatments, which gives us a high confidence in this parameter. But as I mentioned earlier, the objective of this presentation is to show how additional knowledge can be obtained from consideration of other parameters. In this slide, we're now looking at the wet state break extension results of the same bleached hair samples that were shown previously. Results perhaps unexpectedly show the break extension increasing with higher levels of oxidative damage. Perhaps it may have been expected that weaker hair would break faster and at lower extensions, but simply handling and tugging on individual fibers illustrates the more plasticized state of this treated hair. And so to go off on a tangent for just a moment, this occurrence is behind my disliking for another parameter that is sometimes encountered in the mechanical testing of hair, and that is the break work or the break energy, which is represented by the area beneath the stress strain curve. But clearly this is a convoluted parameter which is dependent on both the break stress and the break extension. And so what happens if a given treatment changes these parameters in opposite directions, as we've just seen? And so this slide shows wet state break work results from testing of the same bleached hair samples as before. You'll recall that significant and pronounced trends were seen in both the break stress and the break extension results, but because these changes occurred in opposite directions, break work results suggest little meaningful change in this parameter, which wrongly could be construed as there being little change in the hair structure. Clearly this is incorrect, and this is why I think conclusions based on this parameter can often be misleading. And so returning to the topic of break extension results. While bleaching of hair leads to an increase in the break extension, the graph on the right now shows how heat treatment of hair with high temperature straightening irons leads to a decrease in the break extension. We said before that changes in the mechanical properties of hair are an indication of changes in the internal structure. And if we were just considering the break stress data, we'd likely generate results suggesting that the hair properties are being degraded to similar extents by these two insults. But the fact that the break extension changes in such different ways must mean that the internal structure is also being altered very differently by these two treatments. Perhaps this doesn't necessarily seem a revolutionary conclusion, as the two insults are just so different. But this said, this graph now shows break extension results for hair that's been exposed to increasing levels of a photochemical stimulus, and shows that the break extension progressively decreases as a function of increasing exposure. It's well known that sun exposure can compromise the hair protein structure and diminish tensile properties, with the mechanism generally being ascribed to photochemical oxidation. Therefore, I think we've traditionally assumed that chemical oxidation and photochemical oxidation likely impact hair structure in a similar manner, the only difference being the source of the oxidating stimulus. But consideration of break extension results shows polar opposites in the response to these two insults and must indicate that the internal structure has been impacted differently. And just to show another example of a differing response in break extension as a function of treatment, here the graph on the left shows an increased break extension as a result of treating hair with a conventional commercial relaxer product, similar to what we saw with the bleaching treatments, while the one on the right shows a marked decrease in break extension as a result of treatment with a formaldehyde-based Brazilian keratin treatment. Again, the chemistry taking place is presumably quite different, but the response to the break extension is indicative of differing effects taking place within the internal structure. Indeed, results associated with the formaldehyde treatment are especially interesting as the break extension decreases just so precipitously. So now we're looking at wet state Young's modulus results for the same bleached hair samples that we've been discussing previously. We know that oxidative damage to the hair protein depletes cysteine concentration and therefore diminishes the number of strength supporting bonds within the hair. And so as we've seen, the break stress decreases significantly, the hair becomes decidedly more pliable as evidenced by the increase in break extension, and here as expected we see the Young's modulus decreasing quite dramatically. The 6% bleach treatment lowers this wet state modulus by around 20%, while the 3 times 9% treatment drops this parameter by about 45%. And in general, it's relatively common to see a greater magnitude in the percentage drop of the wet state modulus as a function of treatment as it is for the break stress, where perhaps you'll recall from earlier the wet state break stress for these two treatments dropped by around 12% and 29% respectively. But now on the right, I'm showing the dry state Young's modulus results for these same hair samples, where the extensional stiffness, if you will, of the dry hair actually increases as a result of these chemical treatments. This is especially perplexing as we'd expect diminished tensile properties to accompany a reduction in the number of strength supporting bonds, as is seen in the wet state. But remembering that the wet and dry state tensile properties are associated with different regions of the hair structure, then these results imply that something must be happening to enhance the contribution within the amorphous matrix protein. The crystalline alpha helical structure is being disrupted as evidenced by decreasing wet state properties, but something is happening in the matrix to override these effects and raise the modulus still more. And from the graph on the right, it might appear that the effect plateaus as the 6% and the 9% bleaching treatments give similar absolute values. But in reality, the effect after 9% is still greater as it's had to override a larger decrease in the alpha helical structure to get back to the same point. Actually, this effect turns out to be rather common. Here on the left, I'm showing dry state modulus results for photochemically oxidized hair, which also leads to a similar increase in this parameter. Furthermore, on the right, we see heat straightened hair producing a similar effect. And further to this point, on the right, we can see how the dry state modulus is also raised by a formaldehyde-based Brazilian keratin type treatment. But from the graph on the left, it perhaps appears that the dry state modulus is not impacted by high pH relaxer type products. However, this initial observation hides a considerably more complex story in that the wet state modulus shows an approximate 40% reduction in this parameter as a result of the same relaxer treatment. So clearly the effect we've been talking about must also be present here too, in that this phenomenon, which is occurring in the amorphous matrix protein, has had to override the sizable decrease in the contribution from the crystalline protein just to get back to the same point as the control. It's hard to come up with a hypothesis to account for what's happening here. I've heard it suggested that chemical oxidation produces more charge groups within the hair, essentially cysteic acid, which could then participate in an enhanced degree of electrostatic bonding. However, to me, any additional electrostatic bonding would be created at the expense of losing stronger covalent bonds, which just wouldn't seem to net out in an overall positive effect. Moreover, this effect also appears to be obtained from insults which do not produce oxidative damage and the accompanying increase in the number of charge groups, such as heat treatments, Brazilian keratin treatments, and high pH relaxers. But while it's difficult to come up with a good hypothesis, presumably this increase in the mechanical stiffness is consumer perceivable and becomes part of the overall changes to the properties of hair that arise from such treatments and which fall under the all-encompassing consumer term of hair damage. So we've been talking about differences in the properties of wet and dry hair, but clearly these two states represent extremes with a whole spectrum of conditions existing in between. It's well recognized that the overriding factor that dictates the water content of hair is the relative humidity of the surrounding environment, where hair absorbs more moisture when the humidity is high, and vice versa. Therefore, with water being a plasticizer for hair, the mechanical properties also change as a function of climatic conditions. This is illustrated in this slide, which shows the Young's modulus for hair as a function of the relative humidity of the surrounding atmosphere. As the relative humidity rises, hair absorbs more moisture, the fiber becomes more plasticized, and the modulus declines. And while this is a nice systematic graph, I think the way it's generated also merits some attention. The graph on the previous slide was generated using a smaller standalone diastron tensile tester, such that it could be housed inside a benchtop environmental chamber, and all measurements were performed on the same set of 50 fibers. We talked earlier about the 15% force index approach and its benefits in terms of reduced variability associated with performing before and after experiments on the same samples. And in this instance, fibers were only extended out to a 5% extension, which allowed the evaluation of the modulus without any meaningful disruption to the hair structure. And in this instance, rather than soaking the hair to reset the mechanical properties, we found that the same end result could be obtained by allowing fibers to sit at 90% relative humidity for a prolonged duration of about 4 hours. At that point, the humidity could be readjusted to a new value, and after appropriate equilibration time, the experiment could be rerun under this new set of conditions. And gradually, by repeating this process, we ultimately obtain our modulus versus humidity graph. In short, we're combining the advantage of the 15% force index method, which is the decreased variability associated with repeated testing of the same samples, with that of the automated equipment, which is the reduced variability associated with easily testing a relatively high number of replicate samples. And so we get the best of both worlds. And at the same time, the modulus clearly represents a far more fundamental mechanical property than the force at either 15% or 20% extension. Also from this graph, you might notice that there's 3 data points at 60% relative humidity. One which was generated at the beginning of the experiment, one in the middle, and one at the end. And the close proximity gives us confidence that performing of these repeated experiments does not change the fiber properties in any way. So we end up with very high confidence in our results, 1 because of considerably less variability than traditionally seen with this approach, and 2 because we find ourselves comparing trends in systematic curves rather than individual data points. So here you can now see the modulus versus humidity graph for our virgin hair that was shown in the previous slide, and also a comparable graph for our 9% bleached hair. And the complexity in comparing the mechanical properties of the two now becomes evident. At elevated humidity, in addition to the wet state, the modulus of hair decreases as a result of this chemical treatment. However, at medium and low humidity, the modulus of the chemically damaged hair increases. And if by chance testing had only been performed at 80% relative humidity, we would have reached the conclusion that the mechanical properties of hair had not changed. So I think you can see by performing mechanical testing under just one condition, we just get a single snapshot of really what could be a much bigger and more complex picture. Similarly, here we show a modulus versus humidity graph for hair that was exposed to 300 hours of accelerated weathering relative to our virgin control. We showed break extension results earlier that seem to imply that photochemical oxidation and chemical oxidation are altering the internal structure of hair in different ways. We showed earlier how photochemical oxidation also raises the dry state modulus of the hair, but the more complete story given by this graph implies that this stimulus does not produce the reduction in modulus that we see with chemical oxidation at elevated humidity. And so we're presented with another piece of mechanical data that implies that photochemical and chemical oxidation affect the internal structure of hair in different ways. Here I'm showing a modulus versus relative humidity curve for hair that was soaked in a 10% glycerol solution. And we did this in an attempt to illustrate how we might be able to manipulate or change the shape of this curve. Glycerol is a small molecule capable of hydrogen bonding, and so it too can penetrate into hair to induce plasticization in a manner comparable to that of water, but of course to a lesser extent, which is in general what is seen to occur. Clearly, glycerol cannot plasticize hair to a greater extent than water itself, and so we'd expect the treated and the reference curves to converge and to match up at high water content, which is indeed what happens. But we might also expect that the plasticizing effects of glycerol would best show up when the water-based effects are at their minimum, that is at low humidity or very low humidity. But surprisingly, this didn't seem to be the case. And in actuality, at very low humidity, around 7%, the modulus of the glycerol-treated hair appeared to be very slightly higher than the control. You might notice that there's 2 data points for this treated hair at this condition, and so the finding appears to be reproducible. I don't have an explanation for why we don't observe plasticization under these conditions, but I think I might have one for why the modulus appears to be higher than the control. After performing a selection of these types of experiments, it seemed conscientious to go back and check the reproducibility of the original curve for virgin hair. So we performed a comparable set of experiments on another set of 50 fibers procured from a different virgin hair tress, with the results being shown on this slide. At higher water content, maybe from 60 to 70% upwards, the 2 data sets agreed nicely, but at lower humidity we consistently obtained a somewhat higher modulus from this second set of experiments. Again, we have confidence in the conclusions from this approach because we're looking at a trend that is consistent across a range of conditions rather than just looking at any single data point. And as we've said throughout this presentation, the mechanical properties of hair are a reflection of the internal structure. And so obtaining different mechanical properties in what we believe to be 2 healthy virgin hair samples would seem to apply differences in the internal structure. So to follow up on this idea or this hypothesis, it was necessary to perform additional experiments on further hair sources. Yet the hairtressers that we purchased from the supplier companies, and therefore the hair that we'd used in all of our work to date, all consisted of blended hair made up of strands from a variety of donors. In short, our results constituted an average across a spectrum of individuals. For this reason, we wanted to perform experiments on single source hair, and I had some hair in the lab that had been donated by a past intern who have cut off a considerable length of her hair during her stay with us and going to a shorter style. So here I'm showing results from this third set of experiments using the intern's hair, which showed very comparable results to the second set. Continuing further, I was able to persuade one of my technicians to part with a small number of her hair fibers, and we performed a fourth set of experiments. These data points are represented by the yellow curves in this slide, and so it can be seen that experiments 2, 3, and 4 all essentially fall on a very common curve. And it was at this point I began wondering if something had gone wrong with the first set of experiments, which appeared to be becoming an outlier. That was at least until I performed a fifth set of experiments using commercially supplied mixed race hair, which produced a modulus versus relative humidity curve that was higher again than that for experiments 2, 3, and 4. And subsequently I found other sources of hair that also follow in this curve, and so I don't mean to imply that there's anything special or different about this sample of mixed race hair. More work is clearly needed in this area, but it appears that we are indeed measuring subtle differences in mechanical properties of hair from different sources. And I think these small differences materialize due to the very vigorous and albeit rather time-consuming nature of the experiments that we've been performing, which, as we've mentioned, give rise to lower variability than we've traditionally seen, and we've also talked about the benefits of trends rather than just looking at single data points. It also seems that these differences have become better differentiated when testing is performed under low humidity conditions, which is something I suspect is rarely done and could be a reason why perhaps these observations have not previously been seen. And of course, our industry's traditional use of blended hair in much of the testing we perform may also have contributed to masking this observation. And again, differences in the mechanical properties appear to imply differences in internal structure, which, if true, could really be a major paradigm shift in our industry. Before closing, one of the factors I'd like to draw your attention to is the effect of temperature on the mechanical properties of hair. Our automated dice-run tensile testers sit in a climate-controlled room that fixes both the temperature and humidity. But the standalone units we've just been discussing sit in smaller benchtop chambers, which give us the flexibility of changing the humidity for these specific experiments without messing up conditions for others. These chambers generally don't have temperature control and therefore we're at the mercy of the building's conditions. But these don't change significantly on a day-to-day basis, although there might be a 5 to 10 degree drift in the lab temperature between the peaks of summer and winter. We do have a couple of benchtop chambers which can control temperature and humidity, which are not necessarily trivial to use, but which nonetheless allow us to perform the experiments whose results are shown here. Here we performed comparable experiments to those we've described, where we evaluate the modulus of the same 50 fibers under different conditions. But here we kept the humidity constant and varied the temperature. And as can be seen, systematic changes do indeed ensue. Using the method that we've been describing here, we believe we can pick up very subtle changes in the mechanical properties of the hair, possibly changes that have not been detected before. But clearly in performing these experiments, there's obviously the need to iron out any experimental artifacts that perhaps wouldn't otherwise be on the radar screen. The reproducibility of the trends that we've been discussing make us think that they're real and not the result of such artifacts, but we need to keep generating new data to provide additional confidence and additional insight. And so to summarize, we are frequently asked to measure the strength of hair, primarily to determine product-related effects. And for many of us, this involves looking at the wet state break stress and often the wet state break stress results alone. As I hope I've been able to demonstrate, this parameter does indeed provide an able means for quantifying product and treatment effects, but my aim has been to show that this one parameter is not the be-all and end-all, and as hair measurement scientists, we should not forget about insights from other tensile parameters, other experimental conditions, or even other mechanical testing methods. I hope I've been able to show that while common insults all lower the wet state break stress, they can have different effects on, for example, the break extension, which implies that the hair's internal structure must be changing in different ways, information that wouldn't have been evident from the break stress results alone. Similarly, we can see how the wet state and dry state moduli often change in polar opposite directions, indicating how a currently undocumented occurrence must be taking place within the hair's matrix protein structure. When performing mechanical testing measurements, I think we've always thought of fiber moisture content as a variable we've needed to control in order to obtain quality data. But here I'm suggesting that by setting up the appropriate experiments, it can in fact become a probe to deconvolute changes occurring in different regions of the hair structure. Possibly, as we discussed right at the end, the same could be done with temperature. The approach I've described here, where we produce these humidity versus modulus curves, seems to be an especially sensitive probe into things occurring in the internal hair structure, as it combines the benefits of performing experiments on the exact same hair fibers with that of running a relatively high number of replicate fibers. And in doing so, we believe we are detecting and measuring possibly previously unrecognized subtle changes in hair properties and even possibly differences that are inherent to hair from different heads, which really would represent a paradigm shift in our industry. In performing these experiments, it does become even more necessary to ensure that we are ironing out all potential experimental artifacts, and to this end I highlighted the perhaps unrecognized effect of temperature on the mechanical properties of hair. Of course, if different experimental conditions can produce new learning pertaining to the hair structure, then certainly the use of different mechanical testing methods can do the same thing. And to this end, I presented quite frequently on my interest in the tendency for hair breakage under mechanical fatiguing conditions, and my belief on how it makes us think about hair breakage and hair strength in very different ways. There's also seemingly insight to be had from other techniques and approaches, such as torsion and bending experiments. And so, in short, it's gratifying to be able to close by concluding that clearly there's much more room for research in this area. And so with that, all it remains is to thank you for your attention in viewing this video. If you have any questions, any comments, I would love to hear from you. My contact details are given at the end of this slide. So once again, this is Trevor Evans, and thanks again for listening.